4 of you. It's half the class, I guess. Okay. So I think maybe what I'll do is, instead of having lectures next week, because most of the class is not here, I can assign some reading. Also, we have some other video lectures that I've given before. And so what I can do is just send you links to that and have you guys watch those lectures. So that will be, it may be a little bit ahead of what I would normally have covered, but I think it should be okay. So I'll check into which lectures are probably most appropriate and send them to you. I'll also see how far I get with it. So, and then what we'll do when you come back is we'll maybe work out some situations, some cases of problems in that area to make sure that you've understood the material. The other option is I could do like a problem solving session or something. So, all right. So let's see how it goes. Maybe next week. So next week we won't have lecture either way. I'll just either send you guys stuff online or do some problem solving stuff and put it up for you to watch. Okay. I did assign a new homework, but I've also given you 2 weeks to do that homework because I know most of you will be. Okay. So in the last class, we introduced the first order correlation function, which we said V1 of R1, R2, T1, T2 is equal to trace rho T minus R1, T1 T plus R2. And from this first order correlation function, we then defined a normalized correlation function, which is just defined by G1 of R1, R2, T1, T2 divided by square root of G1 at R1, T1 and G1 at R2. And then specifically we saw that if I take some field state psi, that is incoming, put it on a beam splitter and put it then on a detector after interfering with itself, with a copy of itself basically, that goes into the path, the other path, then we saw that the photocurrent I of t that comes out of the photodetector is going to have a term that is dependent on this G1 of t. In fact, we saw that it's going to be psi e minus e plus at time t plus e minus tau e plus t minus tau, which is just like sort of, you can think of as an intensity at those 2 times, plus this term e minus of t e plus t minus tau plus e minus tau e plus t minus tau evaluated for psi. So this term is just the terms that will be proportional to this G1 at t minus tau, right? This is G1 at t minus tau, and this is G1 at t minus tau among t minus okay. So if the first order correlation function vanishes, then we have no classical interference, and you can check for yourself in different situations when that would occur, and that will tell you whether you get interference or not. Let's see here. I think that's it. Okay. Now we introduced the. So this is how you. I guess what I was trying to say is this is how you measure the first order correlation function, which we also covered in the classical optics part when we were looking at Michelson interferometer. That the first order coherence is what you obtain from a Michelson interferometer. The second order correlation function is just a generalization of that result, G2, and now of course you're going to have 4 indices. Trace, rho, E minus, R1, T1, E minus, R2, T2, E plus, R3, T3, E plus, R4, T4. Right, I mean, I was going to say, I encourage you to try, and maybe I'll assign a problem to also calculate what happens to different states of the field in the first order coherence. And you'll also do some second order coherence that's already in one of the homework problems. Okay? We say, and in normalized form, we call this G2 with the subscripts 1, 2, 3, 4 is defined as G2 1, 2, 3, 4 divided by, as you could expect, G1, the first order correlation function, because that's proportional to the intensity as we saw at all of these different locations and time. So that's a square root down there to take care of that intensity. So I removed this dependence on instead of writing bracket R1, R2, R3, R4, T1, T2, T3, T3, T4, I just put it in the subscripts 1, 2, 3, 4, and you can then write down this correlation. So one of the exercises you have is, for example, to show for a coherent state, so for a coherent state, and I only ask you to do it for a single mode coherent state, okay, you can show that G2 is equal to 1. Okay? So G2, which represents this coherence, the second order coherence or second order correlation function, is 1 for a coherent state. And in fact, like when we typically will measure, so let me just jump to like how we measure it. You take the input state psi, okay, which you're trying to find. You put it on a beam splitter just like before, but now instead of taking it and interfering it after some distance, so remember in this case, if this path length was delta L, the tau was delta L over C, right, over here. And here what we do is we have 2 detectors, I1 of T and I2 of T. And either electronically or through some optical delay, whichever way you want to do it, you can take these 2 signals and you can calculate this product which is the correlation between I1 of t and I2, which is time delayed with respect to itself, and then of course we want to divide that by this guy. Okay, and this is G2 of tau. I say approximately because we sometimes we are assuming that this time average is going to give you the same as the sort of average of these correlation, or the trace of this correlation function. So essentially you can think of this as taking a copy of the field and time delaying it, and then calculating this intensity correlation function between the two arms of the, or between the two signals, and you can think of that as essentially the way we usually do it is if these is an incoming light, you can think of this as a joint probability to have a photon at time t and also at time t plus tau, right? So there's a probability to have a photon both at the time t and at the time t plus tau. Okay. For obviously for a single photon state, right? If tau is 0, right? Then we already saw that the photon is either in one detector or the other. So G2 of t will vanish because there's no probability for tau equal to 0. So for a single photon, G2 of tau at tau equal to 0 is 0. Okay. So if I look at the, let me show it on this side. And I already claimed G2 of tau is equal to 1 no matter what tau is. Okay. So this is another result that you will have to show. It's not so hard to show it. In fact, I'll demonstrate in just a second what is happening for a single mode field. So G2 of tau now, not from the experimental side, but from the definition that I just wrote here. You can see this is in normal order already. All the A daggers are to the left of the A's in this relationship. So we can represent that as the expectation of two normal order terms, I of t and I of t plus tau, divided by the I of t modulo square. Okay? So by normal order I mean, so I of t, of course I would write normally, let's say I of t, right, would be just E minus E plus, or E plus E minus, it doesn't matter, at time t. And I of t plus tau will have a similar relation with E minus and E plus at time t plus tau, right? Which you've already seen expectation, right? What I'm saying here is that by taking the normal ordering, then I get exactly that result over there, where I move the E minus over to the side and bring it all into normal order, and I write it in this form, which is very similar to the experimentally obtained value I1 of t and I2 of t plus tau. Okay? Where I1 and I2 there represent sort of the currents coming from the photodiode, but we know the currents coming from the photodiode will be proportional to the intensity of the light that's hitting each of these photodetectors. So I'm sort of putting the G2 of tau in the same type of form, okay, which comes from here, and I've just sort of rewritten it in this form here. Any questions? That is the most general form, of course, R1, R2, R3, R4, but here obviously two of those are identical. So between say 1 and 3 are identical, 2 and 4 are identical to each other at the time t and t minus tau, or t plus tau. So, questions about this definition? Okay, if you will probably come up with some questions after thinking about it. G2 of tau, now I can write now for a single mode field, so in normal ordering form, it's a dagger of t, a dagger of t plus tau, just like I said, okay, and then the a of t plus tau, a of t side, okay. So we said over there intuitively that G2 of tau equal to 0 for a single photon state should be 0. We can now derive that from this result for an n photon state. For n photon state at tau equal to 0, we can write n a dagger, n divided by n a dagger n whole square. And this, using the commutation relation, you can then write that as n a dagger minus 1 a divided by n squared, and that is just n squared minus n divided by n squared, which is 1 minus 1 over n. So for an n photon state, the G2 at time t equal to 0 or tau equal to 0 is given by 1 minus 1 over n. Okay? And so obviously for n equal to 1, which is a single photon state, then that agrees with the intuitive idea that we had over there, that the G2 at tau equal to 0 must be 0. But now you can see for a 2 photon state, it's going to drop from, it's going to increase from 0 to half. Okay? For a 3 photon, obviously 2/3, and so very quickly as n becomes larger and larger, this G2 of 0 is going to approach 1 for a coherent state. So for example, if you can also ask what about the time dependence? Well, that of course depends on sort of the behavior of the photon field that's coming in. But for example, at time, if this is tau and this is G2 of tau, right? We see if you're truly in a single photon state, it should be at 0, and you might see something like behavior like this. So this is one possible sort of G2 of tau that you would see. Eventually it will approach the limit 1 as tau increases. The reason for that is if you have some spacing of photons, let's say the photons come in equally spaced at some time, right? Then, of course, at time, if you take this and take a copy of itself at some later time, right, I've just displaced everything by some time tau, then there's zero probability to see a photon at time tau equal to 0 again on this graph. But as this this copy of itself starts to approach sort of the repetition limit, you're going to have a unit probability to see the same copy of that photon at a later time tau. So this is one way in which you could get back to the coherent state sort of picture, where the probability going to be 1, the joint probability to observe 2 photons in each of the individual detectors. You can also see sometimes, things like that. This happens, for example, if the spacing between the photons is a bit unequal, if it has especially long times, for example, then it may be that there are some sort of overlaps between previously emitted photons, or if the photons have very long intervals in between them, then you can start to see sort of bunching from previously emitted photons that happen to arrive again at shorter time interval than you would have expected from the last one. Those are typically what happens when we, just to give you an example, you might have a dark state with that an atom has been prepared in, and then once in a while the dark state will emit a photon, so you'll have a higher probability to observe the photon when you emit from the dark state, for example, and that might give rise to a bump in this G2 of tau. But again, it's probably easier for me to show you this with an actual physical model, what is going to happen, but these are some examples of G2 of tau that you'll observe in the lab when you measure it. Okay? Or we can work through some example maybe in the class. So the other thing I want to discuss now, besides the second order correlation function, which I promised, is how do you tell between coherent states and squeeze states? Because in photo detection, with this G2 of tau, it's actually not possible to tell the difference between a squeeze state and a coherent state. Okay? That's just because of the way these operators are written. As you can see, they don't have any phase, so to speak, that you could extract from them. And as we know, to tell the difference between the coherent and the squeeze states, we need to have phase measurements. Okay? Photo detection, as you can see, is purely dependent on the intensity of the light, right? So when the light stream hits a beam splitter and goes into the one detector or the other detector, the output of those photodetectors is proportional to the intensity or the number of photons in each of those modes, right? But it doesn't tell you anything about the phase of the light field in that mode, right? As you can see from both the definition and also from the physical picture, if you have a photodetector, it doesn't know anything about phase. It just takes the incoming field and finds the intensity as we saw, and reports that in the current. So direct photodetection counts photons, right? It counts the number of photons n at time t. Okay? How do you measure the quadrature component, which is x and p? Remember, for a coherent state or a squeeze state, we need to know x and p, which cannot be found from this photodetection process, okay, which only reports on the number. Okay? Even in the best, so for example, the newest generation of photodetectors, which are the superconducting nanowire detectors, they are number resolving photodetectors, as I said, but they still don't tell you anything about the phase of the field that comes in. Okay? So finding the phase of the field requires a little bit more trickery. Now in the microwave domain, this is actually very simple. For a very, very long time, there were these things that have been available, which is called mixers. Okay? If you take a mixer and you take a photodetect, so in the microwave domain, for example, So this is microwave. What you do is you take your incoming signal, okay, S, and you have a mixer, okay, and you put in what we call the local oscillator, okay, which may be at some frequency omega LO, maybe your signal is at omega S, and you get an output, right? And the output is proportional to, let's say, if this is some omega ST, this is cosine omega ST times cosine omega LO T, right? That will be the output of your photodetector. Oh, and of course, I can now add in, phase, for example, phi S, and I can also have some phi LO. And you can see now that the output, once you do the trigonometry, right, you're going to have terms that are proportional to the product, the sum of the frequencies and the difference of the frequencies and the phases, right? So, and if you set, for example, the signal and the local oscillator to be equal to each other in frequency, right, then of course the output is purely proportional to the difference between the difference of the frequencies, the DC component, okay, is of the phases. Sorry, easy enough to write. Let omega S and omega LO be equal. Then the output is cosine, say, phi S minus phi LO plus some terms that are going to be at double the frequency, right? Or maybe it's sine, whatever. Use the trigonometric identity, okay? So the point of that is that we can immediately obtain the phase difference between the local oscillator and the signal, which of course is also going to tell us the X or P part of the coherent state, for example, right? Because in a coherent state, we need either the part that's in phase. Remember, the coherent state has the part that's in phase and the part that's out of phase. With the, if you remember, when we wrote down the electric field, we wrote X cosine omega t plus P sine omega t. And so that could be represented in the X and P quadratures. And so I'm saying, with the microwave, it's very easy to analyze those things because we have this beautiful component called a mixer that's available for us in the microwave domain. Am I right, you guys, from microwave people? Good. But in the optical domain, unfortunately, I should not have erased that. Shut up. Okay. Well, I started this. Okay, hopefully you all know this anyway, so I'm just reminding you about mixers. In the optical domain, things are not so easy. We don't have a way to just directly take two optical fields and mix them. Well, there are some ways. They are using nonlinear crystals, but they are very weak. It's much harder to do this experiment. Okay, so what we do instead is to use these properties of the beam splitter and photodetectors. Okay, so we take again a 50-50 beam splitter, and again we send in what we call the local oscillator, which I'm going to denote now in the quantum field with the operator BLO. Okay, and then I take my signal field A, which is the input signal field that I want to analyze, which is in some quantum state. In the Heisenberg picture, this is just the A that I'm looking at. And then I take the output, again I put it on the two photodetectors. Okay? And then, here's the interesting part, which is actually quite similar to what I did for the mixer. I take the difference between these two currents. Okay. I1 minus I2. Okay? So each of these, this is I1, current coming from photodetector 1, I2 coming from photodetector 2. We can call these arms as A1 and A2. And of course, you already know, we discussed this many times before, A1, which is the output of the beam splitter, is a combination, a linear combination of A and BLO, right? And I've chosen here the symmetric beam splitter, where I put in the phase I here. You could have chosen the real beam splitter, it doesn't matter. That's just going to change the phase that we end up with, the initial phase, but we can vary that. Okay. So those are the two components, and the detected photocurrents I1 is equal to the state of the field E1 minus E1 plus at psi, which is going to be proportional now to psi A1 dagger A1, right? So this one obviously counts the number of photons in the A1 mode, and I2 is going to count the number of photons in the A2 mode. Okay, and psi is the joint state of the LO and the signal. So it is psi signal tensored with psi LO. Okay, right? Because clearly we have both modes coming in, which is just like you remember when we did the beam splitter with incoming photon states. We had one photon state coming in and a vacuum coming in the other arm. We wrote that as 1, 0, right? And so I'm doing the same thing, but now I'm allowing the state of the signal and the local oscillator to be very different. They could be, like, for example, the local oscillator, as you see, is in a coherent state, for example. Okay. The local oscillator is typically a laser, which we can put in the coherent state and send it in. So this will be usually just some psi, which I will call psi A or alpha, or no, I won't call it A. A representing the state that corresponds to this mode, psi A, times alpha for the other. Okay. So the local oscillator is in the coherent state alpha, and the signal, the field that I want to analyze, is in the state psi. And now I want to show you that in fact this output photocurrent is going to be proportional to the two quadratures of the field. Okay, so we already wrote down what I1 and I2 are. So I1 minus I2 is proportional to A1 dagger A1 minus A2 dagger A2, right? Which is just the expectation of the number operators in those two modes, N1 and N2. Okay, so N1 is A1 dagger A1, which straightforward is just A dagger A plus B LO dagger B LO plus I over 2 times A dagger B LO minus B LO A, right? Just substituting definitions for A1 and A2. This is A2 dagger A2, okay, which is just A dagger A plus B LO dagger B LO plus or minus I over 2 So you see the mixing has happened. The mixing between A and B has happened in this term over here, okay? But it is riding on top of this big giant thing, which is the combination of the fields, BLOs, which is the number of photons in the B, in the local oscillator, and then of course the number of photons in the state psi that you want to analyze. But clearly when I take the difference, this term will be subtracted out. So I1 minus I2, so N1 minus N2 is simply I times A dagger BLO minus BLO dagger. Expectation now in the state, in the local state between psi A and alpha L. Okay, so I substitute in that in this expectation value. So wherever I see B yellow, I can replace by alpha, right? Because that's what the state of the local oscillator is in. And wherever I say B dagger, I replace by alpha star. So this guy becomes, in this state, is simply I alpha A dagger minus I alpha star A in the state now, which is just psi A. Okay? And now what I do is, it depends on what this alpha is, right? So let alpha be some complex number, S over 2 times E, which I'm just choosing, minus I S over 2 times E to the I beta over 2. Because I can choose, or I can write down the coherent state of the field as this complex number. And when I do that, and I substitute that into this, I get, this is S over 2 expectation AE to the minus I beta over 2 plus A dagger E to the I beta over 2 in the state psi. And remember that the quadratures X and P are just combinations of A and A dagger. Okay, so for example, in the original definition, X hat is just A plus A dagger divided by 2, right? And P hat will be A minus A dagger, right? With maybe some factor of I in there. Okay? So by choosing this phase beta, right? So if beta is 0, then I recover the X component. If beta is pi, right? Then this becomes e to the minus I pi over 2, which is just minus I, and that is plus I, and then therefore I recover the other quadrature p hat. So what this says is, if I have good control over the coherent state that is coming in, which is essentially the amplitude and the phase of the incoming field, the laser field, I can recover both quadratures, and this is just some proportionality factor S. Doesn't matter for the measurement. It should be as long as it's the same for both X and P, then we are good. Okay. So by slowly changing the phase of the local oscillator, and we can change the phase of the local oscillator, for example, by changing its path length, right? Because the path length of the local oscillator feeds into for an optical field, right? You can just change the path length of that, or you can put a phase shifter, a piece of glass, for example, will change the path length, right? And that will make the laser field have a different phase. So if you can control that path length well, so obviously the path length is important. If you have to control it, you can't let it fluctuate, all that stuff. So those are all important experimental factors. But once you take care of that, if you can solve those problems technically, then you can recover both the quadratures of the incoming quantum state. Okay? And so, for example, if the incoming quantum state is also in a coherent state, you should be able to use this to measure what that incoming coherent state is. Or if it's a squeeze state, then you can tell the difference between the coherent state and the squeeze state by looking at, for example, the variance of the noise. So typically what people do, we are not so interested in actually determining, let's say, the coherent state or whatever. We may want to see the difference between the coherent state and some squeeze state. So what we'll really be looking at with I1 minus I2 is the noise in I1 and minus I2. Because remember, the difference between the coherent and the squeeze state is best exemplified by the difference in the noise, in the uncertainty blob, between the coherent state and the squeeze state in the different quadratures, right? And so this is a way to measure that noise in the different quadratures. So we would look at the noise in this I1 minus I2. We would set all these detectors and currents in such a way that it cancels out all the average values and just gives me the variance of that noise. And then you put it into a very high quality like spectrum analyzer or something and like beat down the noise extremely low and look at that and see what the noise levels are and so on. And so obviously people are very sophisticated about how good these detectors have to be right? These detectors should have a low noise, they should have high bandwidth if you want to look at a range of frequencies and so on. So all those are important parameters. Obviously, any noise in your laser will be bad. So typically, most lasers have like noise at low frequencies. So you try to move the measurement window out to high frequencies, maybe like a few kilohertz or 100 kilohertz or megahertz. If you can get out to megahertz, most lasers are extremely quiet in terms of the noise amplitude from the laser fluctuations, right? So if I look at the laser fluctuations in here and you plot them as a function of frequency, once you get out past a megahertz, lasers are extremely quiet as well. So they approach very much close to the coherent state Poisson statistics once you get out there. So you need reasonably fast photodetectors, electronics, etc. that can respond to those fluctuations, and then you can very much approach the short noise limit and approach the quantum limit, in this case, of the measurement for the quadratures of these two fields. So, any questions about this? This is called balanced homodyne detection, by the way. Balanced homodyne. And this again comes from the microwave terminology. You can see the balance part, that's just two detectors. So the two detectors are balancing out each other, I1 minus I2, so you subtract them. So that's called balance. And homodyne is because we are assuming that these guys are at the same frequency, right? Just like we did for the microwave situation with the mixers, we set omega signal equal to omega LO, because of course that would be the other way to vary the phase between them. But then of course there will be a time varying phase. So there are some clever schemes which do that as well. So for example, if LO is not quite exactly at the signal frequency, but slightly away, detuned from it, then of course the frequency will vary as a function of time. The phase will vary as a function of time, because the two states will have different frequencies. So obviously one will have a different phase than the other as a function of time. And you can use that also to calculate, to find all these various quadratures. Basically you can sweep out the entire quadrature plane by just looking at that variation. You have to be a little bit more careful with that. That would be balanced heterodyne detection. Okay. So people do that as well.
So in this one shot of the measurement, you can only get information about
one phase.
Either X or P.
Correct. Right. You have to switch the phase to get X or P. Exactly. And that's why that other technique is sometimes useful, where you slightly detune the local oscillator, because then what you do is, in one measurement, you sweep out the entire plane, right? If the two are slightly offset, now you can just wait till delta omega times t is pi over 2, and now you measure again, and that gives you the other phase. You don't have to change anything in the setup, for example.
Yeah, but still, even in that,
it's not at the same time. It's not at the same time. But we know that's true, right? X and P cannot be measured simultaneously at the same time, right? So we always want to measure at two different, say, times or something like that. We are assuming stationary light fields, etc., etc. So nothing changes on the time scales of the experiment, right? And that was all assumed in this sort of, when I took the expectation values and things like that. So anything like that where things are changing in real time and you have to worry about that, then that's a separate set of factors. Maybe what you do is you take this and you put it into another setup, right? You split it, you have another part of the local oscillator coming in, you make two simultaneous setups, so to speak. But then you are mixing it in with vacuum fields, so you have that problem. You have additional noise, etc.
Yeah, I ask this because when we do measurement, we can always extract the
X and B simultaneously.
IQ pair. I was thinking what's the difference here. So in this, you can only get.
So how do you get I and Q simultaneously? Because you're splitting it, sending it to two separate mixers. You see what I'm saying? Inside, right, you have a 50-50 splitter to your signal. send it to one mixer with local oscillator. The other mixer goes through, the other part goes through a pi/2 phase shifter, goes through another mixer. So this is how you extract I and Q simultaneously. So I'm saying do the same thing here also. So I put in yet another beam splitter, okay, and then send that beam splitter output to another exact similar thing with the local oscillator, but now the local oscillator is say shifted by pi/2, for example, or you shift the quantum state by pi/2, whichever way you want to do it. The problem is once you get to, I don't know about quantum in your situation when you do your beam splitting or however you do this I and Q measurement. I'm not quite sure, you haven't explained it fully to me, but I'm assuming that's how you do it. Is that how you do it?
I guess we take the raw data. I think the thing of your beam splitter happens.
Oh, the other issue is you have the raw data. You can actually observe your microwave field in real time, so to speak. Right? We can't. Right? At optical frequencies, nothing responds at the frequency of the microwave, or of the optical field. Yeah, we are always time averaging the response. Right? So to obtain the phase, we have to do these tricks. So the problem with having another beam splitter and then the LO and all that is that now you introduce a place where a vacuum field can come in, right? So you do have that problem if you're down to single photon fields or something. You're introducing an additional noise or something like that, into the system. Okay. Yeah.
I'm actually curious, like when you mentioned about the offset of the local oscillator. So like assume.
Sorry, offset what?
The local oscillator.
Yes.
Yeah. So like I make a detune like 10 micros.
Yeah.
And then I just like read the signal for like 100 nanoseconds.
Yeah.
And then
If you can acquire that data, then you have all the quadratures right there.
Okay, I see.
Yeah.
So I
In
just
each data point there,
that will be include both X and P.
will include both X and P.
Yes.
But as I said, it's still at different times. I mean,
Yeah.
You're still, you're essentially initially you're measuring along x-axis, and then because you're slightly detuned, your frame of reference is rotating
Yes.
relative to the original frame of the quantum state, and now your axis is now coinciding with the p-axis, for example.
So when you do this, you assume the measurement time.
Yes, you have to have very good measurement.
It's slower.
It's slow compared to
faster than
that.
the-
Yeah, it's faster compared to the time difference or the frequency difference, 1 over the frequency difference. Is this making sense to everyone? This discussion? Maybe. These guys are very intimately familiar with coherent state measurements, and I think they may be a little bit. Maybe this is something you can teach the rest of the class about in the presentations, how you make these measurements for microwave quantum states, right? I think that would be interesting for everyone. Okay. So in the next part of the class, I want to go into something that I said we would do, which is to discuss the Wigner-Weisskopf theory of spontaneous emission. So we have essentially completed sort of our discussion of states of light, right? Remember I said we wanted to discuss what is the state of a photon, how do you distinguish between, say, a laser, and suppose you had a black box which was emitting single photons, or you had a black box that was emitting a laser, or you had a black box that was emitting, thermal states. Now you know how to distinguish between those various situations. You can look at the photon statistics, you can look at the G2 correlation function, which tends to be more robust than looking at photon statistics for various reasons. Let me give you a reason. So if you want to, right, we already said we could distinguish between, say, squeeze light and between or sub-Poissonian light and Poissonian light and super Poissonian light. Well, that requires you to measure photon statistics. And of course, measuring photon statistics, the problem with that is typically there is the statistics or the noise of the incoming light field, but then there's also the statistics of your detection process, because no detector is perfect and you have additional electronics noise. So whenever you try to claim something about the state of the incoming photon field by looking purely at statistics, by statistics I mean just measuring sort of the time of arrival of different photons and saying, okay, I had n photons, this is the n distribution, so this must be thermal distribution, or this is a Poissonian distribution or something. You can do that, right? The problem with that, as I just explained, is you could have a perfect incoming single photon field, but if your detector is imperfect and misses some of the events, then it begins to look like a random Poisson statistics with some small n bar. So if you think deeply about how to measure these things in the presence of imperfect detectors and noise in your detectors and so on, then you immediately see that something like correlations like this or like the G2 correlation function turns out to be more robust to those kind of effects. Because then the imperfections in the detectors are the same for both detectors. Let's say these are balanced detectors and so on. Then you can take into account all of these situations, plus the G2 of tau relies directly on the quantum nature of the field to obtain, say, that result I showed you earlier where G2 of 0 is 0. It doesn't rely on, say, knowing some statistics about the incoming light field. So it's a more sort of robust way to measure these things. Still, of course, you have to worry about imperfections in the setup, how well your photon counting boards are working, and whether they're measuring things that you want them to measure. All that is still an issue, but those are technical problems that are well solved at this point. Okay, so what we are moving on to discuss is the Wigner-Weisskopf theory of spontaneous emission. So now so far I was only considering the Hamiltonian for a quantum field, right? Which is, we saw that the Hamiltonian for the electromagnetic field is just h bar mu k lambda sum over k lambda times a dagger a k lambda plus half, right? Well, now I'm going to bring back the atom into the situation. So remember the two-level atom, okay? So we had 1 and 2. These are the two states of the atom, and we said that the atomic Hamiltonian is very simple. If you take the 0 of the energy to be here at the state 1, then that is just h bar omega 2, right? So we have the two parts, the atom Hamiltonian, the electromagnetic field Hamiltonian. Remember here we are not driving it with a classical state. Okay, we could also include that by assuming that there's some incoming laser field. We're simply taking an atom coupled to the electromagnetic field that exists, and let's imagine that this is existing in some universe with some volume V, and then the electromagnetic field, we already wrote that down, is at the point r comma t is the sum over k lambda square root h bar mu k 2 epsilon naught v, and this is the quantization volume, which is usually we're going to take it as very large, although later on we can modify that and see what happens. Okay. So again, to remind you, this is wave vector. This is polarization lambda. Mu k is the frequency. Mu k equal to c times the wave vector amplitude, right? The magnitude of the wave vector. V is the quantization volume. And usually V is going to go to infinity at the end of the calculation, or just to think about the states, they are very finely spaced in a continuum approximation. Okay? And ek lambda and ek star lambda, these guys, sorry, vectors, I guess. These guys are polarization unit vectors, which of course depend on k and lambda. Okay. And now we need an interaction between the atom and the electromagnetic field. As before, I'm going to directly assume that this interaction is in the dipole approximation, the interaction. So that is just minus mu dot this E. This E now is this operator E rather than a classical field. Right? In the classical case, E was just some classical field which had some time dependence, but now I am explicitly saying that E is a quantum field. Okay? And this mu, again, we have already covered it, is some vector mu with the operator between 2, 1 and then mu star 1, 2. So that represents the dipole moment operator for the atom. Okay. Now the first thing is we're going to get rid of this electromagnetic field Hamiltonian by moving to an interaction picture that is rotating at the field frequency nu k lambda, right? So we have already done this several times in the homework, and we have done this before in the class. So what I'm saying is I essentially take this guy and make it evolve the field frequencies. So the field frequencies now go from being time independent, or the field operator goes from being time independent to time dependent, and I get rid of the energy of the electromagnetic field. And of course, you can make all that formal by just assuming that there is some operator U that is rotating in the with this ak lambda ak with the frequency nu k. Okay. So basically, I'm saying some field. You could call that like a field interaction picture, or there are various names, but the mathematics is pretty straightforward, and you've seen it. Essentially, I want to get rid of this term in the Hamiltonian. So I get that E now, because of that, is now a function of R and T, which goes as summation k lambda, again, it's the same thing, except now ak lambda is going to go as e to the I mu k t times e to the I k dot r, and then there's the epsilon k lambda, of course, plus, I'm just going to write that as permission conjugate. Okay. Okay, and this should look familiar to you, because when we first did the atom field interaction, when we did the classical or semi-classical atom field, we said that E is some E naught e to the minus I nu t plus complex conjugate. Remember? Way back when we just said, let the electromagnetic field be treated as a classical field with some amplitude, and we might have had some phase as well here. You know, we wrote this down, okay, back in week 2 or 3. And we have now exactly the same thing, except that E naught now has an amplitude, but is also an operator. Okay? So we can use the same rotating wave approximation. and keep only the terms which have, when we multiply, for example, mu, right, with E over here, we're going to get 4 terms, right? We have 2, 1 times A, which says that the atom goes from state 1 to state 2 and a photon is destroyed from the field. Okay, that's one type of component. We can also have 2, 1 with A dagger, which means atom goes from 1 to 2 and a photon is also created in the field. Now this is clearly going to be an energy non-conserving term, or equivalently you could call it the counter-rotating term in that old semi-classical field Hamiltonian. Okay? And also the other term, 1 to 2, meaning the atom goes from the state 2 to the state 1, and field is and a photon is destroyed. That also is non-conserving in the energy. But then the term where atom goes from state 2 to state 1 and a dagger, which is in this other part of the Hamiltonian, that part will be energy conserving. So either thinking of it as carrying out the rotating wave approximation or energy conservation, whichever way you want to view it. In this interaction, you can also say those are the only terms in this Hamiltonian which are going to commute with this other 2 terms, or which are going to have this sort of behavior which we call the rotating wave approximation. So in this interaction, Hamiltonian in the rotating wave approximation should have only the terms minus summation A lambda. And now I introduce a new variable which I call G, and I'll write it down in a second. So out of the 4 terms that were in mu.E, only 2 terms survive. And this G now is clearly just mu, the dipole operator, dot product with the polarization of the photon divided by h bar times the amplitude of a single photon field, which we have seen many times now, right, times e to the I k dot r naught, because we had to evaluate it at the position r equal to r naught of the atom. Okay? So that is our g k lambda for the field. Okay. If you had a different type of normalization, for example, if you had some standing wave cavity, then you might change what is sitting out here. There might be some cosine k dot r naught. If you, instead of expanding it in terms of plane waves, if you expand it in terms of some other modes, some Gaussian modes, or some modes of some photonic cavity, or the modes of a transmission line resonator, right? As in a superconducting microwave experiment, then you would have a different factor out in this gk lambda, which depends on the modes of the particular volume in which you are quantizing the electromagnetic field. Okay? But ultimately, all of that just affects this gk lambda and does not play a role as far as the quantum dynamics is concerned. That is just this 2, 1, ak lambda, 1, 2, ak lambda diagram. Okay? Okay, I have 5 more minutes, so or 10, few more minutes. So what I'll do is I'll just set up the problem, and then we'll go through the math, or maybe this is what I'll assign for you guys to look at in the when you're away. And a lot of it, the math will be very similar to when we did. If you go back to week 3 or 4, we did something called the bound to continuum transitions, or the multi-state systems, and we looked at the sort of the derivation of the decay rate and the AC start shift for the situation where one state of a field of an atom is interacting with multiple states as the final state, and we re-derive sort of Fermi's golden rule and the AC start shift. Well, what we're going to see now, I'll give you a preview once you set up the problem, is you're going to see that this problem looks just like that problem, except now there will be a start shift which is known in quantum electrodynamics as the Lamb shift, because it is the shift in the energy of the atom which is caused by the interaction with the quantized electromagnetic field. And that was historically was observed and gave the first indication of the quantized nature of the electromagnetic field, which is seen because there's an AC start shift that occurs due to the interaction with a quantized field and not a classical field. When we did it with the bound to continuum, there was a classical laser field that was driving the transitions. Here, the vacuum fluctuations or the quantized field drives that transition from the state, say, 2 to the state 1. Okay, so now I'm going to put all that back and write down the Hamiltonian of the system without now without this part, the electromagnetic field Hamiltonian, because that has been moved into the dependence, the time dependence of the field of the interaction term. So H is H bar omega Q2 plus or minus, sorry, H bar summation K lambda G K lambda I guess this is I can and if we are now further going to specialize to the situation. Oh, I see. So what I did is, after doing that, now I reintroduce back the original vacuum or the original state of the Hamiltonian of the electromagnetic field. Meaning, what I do is I say, well, this AK lambda e to the minus I nu kt came from that original Hamiltonian for the electromagnetic field, right? Well, essentially I moved to a rotating frame, right? I moved to a rotating frame which was going with this e to the I nu kt, and that got rid of the energy components of the electromagnetic field, because now I was rotating with the field components, okay? And now I see that I have an interaction term. That helped me to understand that it's just like the energy conservation of the rotating wave approximation of the electromagnetic field that we did for the semi-classical state. And now I want to get rid of this time dependence in this Hamiltonian, in the interaction term. So I'm going to put back the dependence on the, because I have to energy conserve everything, and so I'll put that back here again. Sorry, that was a little confusing. I can give you the more rigorous math, maybe in a handout or something. It all works out. You can easily see that. Okay. Essentially, I transform, I look at which terms are conserved in that interaction there. I drop all the terms that are counter-rotating, and then I transform back to put the energy back into the Hamiltonian. Okay. So now this term is again time independent. Okay. that's going to allow me to use perturbation theory and to solve the terms. Okay, I'm almost out of time. So what I'll do is, I'll now say that initially we're going to put in an initial condition. If initially psi atom equals the state 2 and psi field equals, so normally you would have to write this as sum over all possible k lambda of the nks, right, nk lambda. Basically that's how you would write it, some f, which is a function which tells you all the components in the different, but instead I'm going to say we started with the field in the vacuum state, 0. Okay? So with this condition, we can immediately see which terms in this Hamiltonian will have non-zero matrix elements. So if you are in the state 2, 0, right? If you are at 2, 0, then as I already showed you, because of these terms in the Hamiltonian, you can only get to the state of the form 1k lambda, which goes as ak lambda dagger of 1, 0. Okay. So we have only these possible transitions. Don't have to worry about any of the other terms in this full expansion. So I can write down in this truncated Hilbert space, okay, in this truncated Hilbert space, I have H equals H bar omega 2, 0, 0, 2 plus summation over k lambda H bar new k lambda 1 k lambda 1 k lambda minus summation over k lambda of H bar times gk lambda times the states that go as 2, 0, 1 k lambda plus H bar gk lambda star 1 k lambda 2, 0. So to make the connection between our earlier treatment of bound to continuum transitions, I'm going to call the state 2, 0 is going to look just like the state B, which is the bound state in my earlier treatment, and 1 k lambda will be just like the state K continuum in the bound to continuum transitions. Okay? Or if you like, you can simply write down the wave function and solve it in this truncated Hilbert space. So with that simplification of the notation, then I've written down that, I'll just write down the equations and we'll stop. So if I write down psi of t is equal to d of t times the state b, which is the initial state 2, 0, plus ck of t times the state k, and then we can put that back and we can write down the equations of motion, and that's what we will do in the next class. Okay? Or I'll ask you guys to watch the video where I show you what is done in this part of the treatment. Okay? So that's all for today.
你们下周全组出动吗？
对对，我们也不去。
哦，
我去。
好的。